Welcome. Welcome to the last session before lunch today. My name is Craig Beardsley. I'm the Director of Power Industrial at AECOM. And for those of you who don't know AECOM, we are technical advisors, designers, engineers, and project managers. And in the energy sector, that means all power systems, including renewables and, importantly, energy storage. So today's session is called How Will Energy Storage Improve Mining's Energy Landscape? And Adrian and the team at Energy Minds have done a fantastic job at assembling the panel here today to explore that issue. And I won't keep you in suspense anymore, and I'll pass on to the panel to introduce themselves. Taylor.
Good morning, everyone. My name is Taylor Sloan. I'm from Fluence, which is a battery energy storage provider. Fluence is a joint venture between Siemens and AES, and we have 500 megawatts of deployed or contracted energy storage, which makes us the largest in the world, across 16 countries and 50 projects over 10 years. So excited to be here today. Thank you.
Yes. Good morning, everyone. Thank you very much for inviting me. And my name's John Pemberton. I'm the General Manager of Australian Operations for COCAM. COCAM is a South Korean company. It's a very vertically integrated battery supplier. We make our own batteries. We make our own systems. We do a lot of work in defence. And so we have a lot of very specialised technologies that are being applied now in the commercial sector very successfully across the world.
Good morning. My name is John Cole. I'm the founder of Edify Energy. Edify is a developer, investor and long-term asset manager of renewable energy and storage assets. We have under construction or in operation 440 megawatts of large-scale solar. One of our solar farms, which was the Gennawarra Solar Farm, is the largest in Victoria and was recently commissioned. And then we, and as is relevant for this conference, structured and packaged up with the support of the Victorian Government and ARENA, a 50 megawatt hour, 25 megawatt Tesla battery that we retrofitted into the solar farm. And we think that's created one of the largest, if not the largest, integrated battery and utility scale PV plants on the planet.
Hi, I'm Sam. I'm from vSun Energy. Our remit is to advance the uptake of vanadium flow batteries, and our parent company, Australian Vanadium, is a mining company, junior miner at PFS stage. You may have seen Vincent Algar on the panel yesterday. We have a vanadium deposit just south of Meekatharra. And so through our PFS at the moment, we're looking at energy requirements. So I sort of have two different hats.
Hi, I'm Greg Allen. I'm the Managing Director for Australia for Hydrostore. Hydrostore is a large-scale, sort of 100 megawatt scale bulk energy storage using compressed air technology or advanced compressed air technology. We're based in Toronto in Canada. I suppose the relevance for this conference is we've just kicked off our first project in South Australia where we're using remnant underground mining assets for the storage cavity for compressed air storage technology.
Thanks a lot. As you can see, we've got a lot of bases covered here with the panel today, both in terms of technology and perspectives. And I think it's fair to say that in the last 12 months since this conference was held, I don't think there's any other technology group that's made greater progress than energy storage, both in terms of cost reductions and technological advancements. In just 12 months, we've seen the largest energy storage battery commissioned at Hornsdale Wind Farm. We've seen the announcement of Snowy 2.0, the largest energy storage project going on anywhere in the world right now. And we've seen numerous other smaller hybrid projects kicked off. So to start things off, I'd like to throw it out to the panel. How do you feel and when will energy storage transform the applicability of renewables for miners?
I can probably take that one. From my perspective, the transformation's already started, and with the uptake of battery energy storage, mainly for spinning reserve applications, that's where they sort of have their prevalence at the moment. And I think over time we should see, in my view, the next 5 years or so, we'll see those applications start to move into generation shifting type technologies for energy storage.
Yeah, I see it as a progression where it's going to start off with spinning reserve replacement as the first step, as the lowest hanging fruit. The next step will be shifting chunks of energy from the day to the night, maybe 4-hour chunks. And then the last step would be really that longer duration, sort of more of a base load type of application. But I see the industry progressing in that order.
Yes, having had experience with the Alinta plant that we've just commissioned, which is a 30 megawatt plant with 11.2 megawatt hours of storage in conjunction with 4 gas turbines. So it really is a true spinning reserve application. It's very, very effective in terms of being able to take gas turbines offline and also to support the grid. It's off grid, but to support the network there, and it has to actually supply power to a remote mine, so down a 220 kV transmission line, 120 kilometres, and we have to be able to operate the protection at the end of that mine as such. So this is really sort of it's been quite a demanding project, but certainly it's shown what the batteries can actually do in respect to emulating a generator. So as far as the grid's concerned, it actually sees the battery as just as another generator. But it's sitting there in standby, just doing a bit of frequency regulation for sort of most of the time, unless it's called upon to undertake a deep discharge if one of the GTs falls over. But what I think is really important to understand is when you're thinking about this, we really do need to understand the issues of like the marginal costs of generation. And I mean, all mines really are going to have fossil fuel generation. I mean, unless you're sort of in that unique area in Chile and can have a sort of solar thermal power station that's going to go 24/7 because it sun's out 365 days a year. Every mine is going to have sort of full capacity in terms of diesel or gas. So then you're really dealing with like what the marginal cost is of, say, gas generation. And if you take gas generation, the short run marginal cost might be about $85 a megawatt hour. Diesel could be $2.30, but the round trip, you've got to think about what the cost of storage is. So there's a round trip cost of storage, and that could be, say, $180, $200 a megawatt hour. So in actual fact, and I'm just sort of building on a point that BHP made yesterday, and that was that actually gas is a really good firming mechanism. So just building on what you were saying, that I think that in the short term, the use of these batteries as spinning reserve is absolutely an absolute no-brainer, and that gas makes an awful lot of sense. And you need to use the right type of batteries with the right type of inverters to be able to supply the equivalent of real inertia. Real inertia in these weak grids is incredibly important, and you need the right system to do that.
As a follow-up question to the group here, it sounds like that transformation is well underway and that spinning reserve is an application which makes sense right now today. What sort of fuel savings are being achieved in these purely spinning reserve type applications, and where could we head as we start to push forward into deeper with more and more penetration of renewables?
I might go again there. I won't try and give any exact numbers, but I know that in our plant in the Pilbara that I'm talking about gas, not diesel, but sort of the saving is in the order of sort of 0.5 to 1 petrojoule of gas per annum, and you can do your own maths, so it's a significant number.
Craig, I think it really turns. We've heard a lot of numbers at this conference. We've heard $50 megawatt hour for solar. We've heard $200 for storage. There's a Bloomberg report out with $300 per megawatt hour for solar and 4-hour storage. but they're just headline numbers. I think everybody needs to look at their project and what are your needs and what's the best system, and there isn't a one-size-fits-all system. I think that if people want affordability, reliability and sustainability, then the technology, including from people on this panel, is there today to provide that. And the actual savings, you need to look at your use cases. There was a presentation this morning to say, well, hold on, work out what you want and then design for that. And I think that's really important. I think people need to understand what are they looking to achieve. The other thing is that a battery isn't a generator. It is a generator, but it doesn't create any energy. It needs to be fed with energy, and then it releases energy. So I think you need to have a look at what fuel source or what do you want to feed that battery, and then how you use it in amongst a generation mix for your project. And for me, there's no doubt that the batteries and renewables do create a compelling argument.
I think you're right with the talking about saying what you want. People often seem to go out for tender and say, I think I need a lithium battery, which is a 2 megawatt, 1 megawatt hour or something, when in actual fact they need to say, these are my energy requirements. How are you going to solve that particular problem?
And in terms of how you actually do this, I mean, it depends on your heat rate curves if you're using gas or diesel. So you can do it yourself. Look at a dispatch, a typical dispatch, and do it once with your spinning reserve requirement being maintained by the thermal generators, and then do a hypothetical, what if I could do this with no spinning reserve? How could I improve my dispatch? How many units could I turn off? And how would the heat rate of the other units improve? And then just look at the weighted average heat rate and see what that percentage is, and that's going to translate to your fuel savings. So, I mean, you can do it yourself. Don't rely on us. We've seen in the range of 2 to 8%, but prove it out for your generation fleet.
The other aspect of that as well is look at the maintenance savings. So if you can switch off a diesel or a gas set, you're accruing costs on hours per run, not kilowatt hours out of that unit. So getting a unit offline and being able to size a system so you can totally turn a unit off. The maintenance cost saving alone will have a large portion of the business case justification.
I think that's part of the problem with diesel, is that people understand the limitations of it and they accept that because that's what they've always had. So maybe they don't need to consider what an energy storage system could put in, and you wouldn't need some of those limitations.
Yeah, those are fantastic points, and as you say, the maintenance side of things is an often overlooked part of the equation. There's been a lot of focus, I think, here when we're talking about energy storage around the off-grid context, as the benefits are fairly obvious, particularly in the spinning reserve applications. What are some of your thoughts on the applicability of energy storage technologies to some of the grid-connected miners here?
I'll kick it off. One of the applications that's not specific to mining, but any grid-connected load that's very large, would be if you can reduce demand charges. So if you have in the range of anywhere above $20 Australian per kilowatt month demand charge, energy storage starts to pencil. And you can think about how that can also stack and provide other benefits like reactive power. Maybe you can avoid like a static VAR compensator CapEx because you've got energy storage, reducing your demand charges and providing other sources to the grid.
And of course, the other thing is the UPS functionality. The grid goes down, so the battery can act as a giant UPS while other generation sources crank up.
I mean, that's a good point to emphasize. I mean, there's been a lot of discussion, I think, around technology risk, and that's just one example where these technologies can actually reduce risk for these mines around reliability particularly.
I think as well just the revenue stack. So there is demand charges that are reduced in playing different markets, ancillary service markets, as we're seeing the Tesla battery at Hornsdale do, and likewise for other aspects. And I think it's really around the use case for the battery. If you're a miner, then and you want to do it yourself and self-perform, then it's really understanding the functionality that these batteries provide. And I don't think that they are truly well understood at the minute, and the whole market's learning, particularly the Tesla battery, as I say, at Hornsdale is leading the way there on just how quickly it can respond. So I think that needs to be factored in. If you're then looking to, with an IPP solution, then you need to understand what those revenue benefits are for the IPP because that should ultimately reduce your total power costs on the electricity side. So I think understanding the way the batteries function on grid and the revenues that they can attract is really important for anybody who's looking for an on-grid solution.
We're looking at applications where essentially we're putting behind the meter solar and coupling that with bulk energy storage to give essentially a virtual base load solution from solar. As an example, you can essentially put 40 to 50 megawatts of solar in behind a grid, add some bulk energy storage, and you're essentially firming up 5 megawatts of baseload capacity. So turning PV into a baseload solution, which has then got the benefits of the demand side, or taking demand charges off. It's also avoiding the penalty of being charged firming charges from the grid operator as well.
I think another aspect, I sort of touched on it earlier, but it's about inertia, and I think we're going to hear a lot more about inertia, and it's certainly touched on a number of times in the Finkel report, and so I think we're going to see a market emerge for inertia services. The beauty about the right battery combined with the right inverter is that it can actually act as a generator and can actually supply real inertia. So you can envisage a situation where the battery is actually not doing anything, so it's not costing anything to maintain, it's not spinning, it's just sitting there, but you can actually be paid for the fact that you can supply inertia on demand as such. So I think that's another interesting value stream. And of course the battery sort of in the grid-tied scenario in the mines can provide sort of that ancillary services to the whole system and very beneficial overall.
In the case of compressed air energy storage, it's traditional rotating equipment, so we're using compressors and turbines to do that generation. So inertia is an inherent functionality. In terms of consumption, I don't think our consumption is drastically different to that of batteries. We would consume about 2% of the rated capacity of the facility in parasitic losses. I think batteries will also have some parasitic losses. Even if they're sitting there idle, there will be some parasitic losses. So I think in terms of equivalent, in terms of compressed air energy storage, we're definitely can provide inertia, and it's traditional inertia, which utilities tend to understand and is well understood in the market. So.
In those traditional inertia type applications, is the value of those types of technologies better recognised in the grid connected environments, or do you not feel it's any barrier with off grid?
Well, I think it comes down to there's a question right at the end here about key criteria. I think impact load response of an islanded grid is something that mining customers are acutely aware of, and that all comes down to the inertia of your system. If you want to get a large mill away, you need a lot of inertia in your system. So whether that's coming from spinning generators or it's coming from batteries, or whether it's coming from other forms of storage, it's got the same applicability across whether it's an islanded system. Generally, it's probably going to an islanded system is going to be more twitchy, if you like, than a grid-tied system.
And particularly with us seeing a bit of a trend towards more use of recips as opposed to GTs in these sort of scenarios, and the recips sort of by definition have considerably less momentum than the gas turbines. So this becomes sort of all the more important in this environment where you're going to see more reciprocating engines, gas engines going in. If we want the optimum mix, then sort of to mix these with the batteries makes an awful lot of sense.
Well, one thing I'd be very interested in is what you feel the challenges are for this group. There's a lot of people here that are probably thinking about batteries, about other forms of energy storage and how they can apply them to their projects. But what are the key factors that are holding them back? What are the key barriers and challenges that they've got to overcome to get one of these projects up?
I think when you go out, like we are at the moment for our PFS, you need to just make it very clear that you want the options put in front of you, and you want all the different options, not just what that particular person favours or what they know particularly well. So we've just obviously put out our energy requirements for Australian vanadium, and of course we specified that we wanted renewable energy in there, and particularly a vanadium flow battery. So it's sort of twisted it round. I started getting phone calls now from the energy people who previously wouldn't look at a vanadium flow battery because they didn't know what it did, and now they're coming to me for a quote because the mining company's demanding, I want that renewable energy component. So that's one of the ways that I think that it could change.
Yeah, I think for me, it's the main one is achieving a cost benefit and a justifiable business case without impacting reliability. That's sort of, I suppose, at the high level, and I think we've seen that come through in the discussions over the last few days, today and yesterday. I think the other one is around the incumbent power provision. Like, where is that coming from? And inherently, if that's coming from an IPP, there's technical and commercial integration challenges associated with anyone other than the IPP coming in to try and provide that service without affecting, I suppose, how the mining company is and who they're managing that risk through. Because ultimately, they want a reliable power supply that's not going to interrupt their operations and cause issues on their system. So I think that is a key challenge, and it's normally going to lend itself to major revamps of power system configurations and generation configurations at the point that current arrangements under independent power producers are coming up for renewal.
It's unpicking those contracts, isn't it?
Just one of the other key challenges is, of course, getting costs down to make the batteries more economic. And we see a lot of sort of projections that look as though it's going to mirror the cost curve of PV and how it came down. Certainly the battery prices have reduced significantly, but I guess a lot more lithium is going to be produced, not sure about cobalt, but what really needs to be understood is that it's not just about the battery, it's actually about the system. So, 40% of the costs can be associated with the inverters and the power electronics, and you've got all the balance of plant that goes with this. So it's not just the cost of the battery, it's the cost of the system. And I'm not sure it's going to come down that cost curve as fast as everybody thinks.
I think that's a common thing I've heard too, where people see the declining cost curve and they say, well, why don't I just wait until next year and it'll be cheaper? And then it comes to next year, oh, well, I'll just wait one more year. It's kind of like with phones. Like you should never buy a phone if that's your position, because it's always going to be cheaper the next year. So you got to look at what are the savings that you're not going to be taking advantage of for that year that you're waiting. So if it's a 15 or 20% return project and you're holding out for a 7% cost decrease, that doesn't really make sense. And at some point, you just have to do it instead of waiting for the cost to be coming down more and more.
You have to factor in, like Louis was talking about, the supply chain emissions. That's going to be a huge thing going forwards. So if you wait and wait and wait, then your supply chain isn't being protected against that.
I think you've just hit on it. It's a bit of a change of mindset is a challenge. There has been a lot of talk yesterday about the technology risk in these systems, and I personally don't see it. I know that a reintegration risk and everything that needs to be put together to replace conventional generation with new generation has a bunch of challenges. But the equipment itself, I think the technology is more proven than was understood yesterday. So I think there's a real mindset change. And then as to economics, yeah, I agree that the battery cost curve may not come down as fast as solar PV has done, but already we're seeing other things that impact the economics. So extended lives of batteries, reduced degradation. Now those things are just as good as a reduction in price, depending upon what your use case is. And as to Taylor's point, again, lots of talk yesterday about mines with shorter lifetimes. If you wait for another year and you've only got a 7-year offtake arrangement instead of an 8-year, you could find that you're paying more. Net, you're paying more, even though there's been a slight reduction in total capital costs. So I think, again, it all comes down to that use case and what's being sought, but delay isn't necessarily the way to a cheaper solution.
Yeah, I think there's certainly plenty of incentive to act now, and I think for anyone who was here yesterday and saw Matt Walden from Arena's presentation, they're here to support those organisations willing to act now, and particularly those that are willing to be bold and push the limits around renewable penetration, which doesn't necessarily increase your risk, and willing to look at the diverse range of energy storage technologies that are available in the market and picking the right one for their applications. So, yeah, there are plenty of incentives for moving right now. So, in terms of what's been happening recently, what do you feel are the recent innovations that are going to really change the way we look at energy storage and the applicability in the mining sector going forward?
Yeah, I think John touched on probably the key one from the battery component, and that's innovation around the inverter technologies. And in particular capacity and functionality that's being offered by inverters, and that's continuing to improve. It does come with a challenge that they make up a big portion of the overall cost of a battery energy storage system. So they do, but they're the brain of the system, and they provide all that functionality. So that, for me, the innovations around that need to continue to improve to continue to offer more services from batteries. I think from my perspective and from HydroStore's perspective, it's around embracing other technologies, whether that be repurposed compressed air storage technology has been around since the 70s, but it's at a price point now and has been advanced enough that it's starting to make sense in terms of the market that we've got and competitive on large-scale applications. Likewise, flow batteries. It's about looking outside, I suppose, outside our blinkered approach of like, this is the technology that we should be applying, and stepping back from it and saying what technologies really make sense if we take a long-term strategic view on what the energy supply mix should be for a particular application.
It's kind of interesting that we've actually got the lithium guys on one side and the bulk storage on the other side with a developer to keep them apart. But I think it's important to note that both couches are very complementary technologies, and they can certainly form together on the same project. As we often talk about hybrids as being storage with renewables, but it's hybrid as storage with other types of storage as well.
That's what they're looking at. Well, that's what they're bringing in to Monash. I know it's not a mining company, but they're bringing in a flow battery and a lithium battery so that they can then draw on the strengths of each of them and have that flexibility there.
Shouldn't have this argument, but we can cover everything.
So can we, but...
But just talking about innovation, one of the clear innovations is the higher C-rate batteries. So these are the batteries that can discharge at sort of faster rates. So we've now got a range of batteries that can discharge at like a 10 C-rate. So that's basically like a 6-minute discharge, very, very fast. And so you can envisage sort of those type of, good for UPS, but also good for very small systems that could be used in conjunction with, say, small recip generators. We put in these very low, very small footprint, very high C-rate batteries.
Going back to your original question, electric vehicles or the hydrogen that they were just talking about a minute ago, I see that as a huge development for energy storage in mine sites as well. And that's where an existing mine can introduce energy storage, because if you've got all your infrastructure set up and you don't want to make that change, if you do go down the electrification of the vehicles, then you can add in some solar and storage to charge those batteries.
Well, I mean, there's a lot of people here who are considering energy storage, as I mentioned earlier, and I'd be interested in the panel's advice to the people here around how to go about it. What are the key criteria they need to be thinking about when considering energy storage applications for their site? Many of you have done exactly this exercise many times before, I'm sure.
I'll kick it off, and then I'm sure there's more ideas, but the useful life or the remaining life on your mine. So if you're looking at under 5 years, it might be tough to do it. Although we have seen 4-year paybacks for the spinning reserve play. Also look at your fleet. I mentioned this earlier, but the heat rate is a key determiner in how much fuel savings you'll have. So looking at the actual gen sets you have and how the dispatch would change with energy storage would be a key criteria.
Do you mind elaborating on that point a little bit for some of the people who don't understand the heat rate concept and how that affects with spinning reserve applications?
Yeah, so what we've seen is if you have a fleet of assets, or maybe you have one really efficient generator and other smaller generators that aren't as efficient, you're not always able to dispatch such that you're hitting the optimal set point or heat rate for each generator, because you're always trying to maintain like the N-1 reliability. So if one trips offline, you have enough room on the other gen sets to be able to ramp up and cover it. But if you're not constrained, if that's not a constraint on your dispatch optimization, and you're able to just use a battery that's fully charged and ready to discharge at any time, you can achieve better heat rates by having the best gen sets running at their most optimal heat point and the least efficient ones turned off. So that's how it works essentially.
You know, in terms of key criterion, sort of when we're asked to size a battery, you know, the mix of megawatts and megawatt hours is obviously absolutely sort of a key criterion. Needs to be understood, the sort of the difference between power and energy as such. So the number of minutes that you want the battery to actually operate for the duty cycle is critically important. So, and that's often very difficult to understand, because, like, say, marrying a battery with solar and using the battery for ramp rate control, well, really, you know, nobody knows sort of perhaps how many cloud cover events are going to happen sort of per annum. So that becomes quite difficult, but it is particularly important in sizing these batteries. And what ancillary services you're going to be wanting to do, like sort of, so, you know, what might the frequency regulation requirements be, because we need to allow some headroom to be able to do that. So because the battery's got to discharge and discharge, so we need to allow a little bit extra capacity to enable that if you want to do frequency regulation. And then the whole concept of the lifetime, so, you know, I'm talking lithium now, so, you know, we do get a very, very small degradation per annum, and dependent on the duty cycle, there is some degradation too. So we do oversize the batteries to start with, so we need to know what lifetime this is actually being designed for. So we might talk of, say, a 10-year end of life, or we might talk of a 15-year end of life, and at that period you may have lost, say, 20% of the capacity. Still be good, you know, but still be very good life left in those batteries. You may surprise yourselves after 15 years. We've taken batteries out of submarines after that sort of time, so, you know, we actually do know how they actually perform. So 15 years in a submarine, it's still pretty good.
I agree totally with John, actually, but you know, when I was a boy, there was a Castrol ad on TV, and it sort of ended, "Oils ain't oils," and batteries ain't batteries. You know, it's what's your use case for these things that needs to be understood, and the functionality that you can get out of batteries, lithium-ion in particular, as a tried and tested technology, has a very broad range. Yeah, and no offence to anybody on my right, but that's sort of what I know most about. But it's just not one function. It's not something that you start and it has a generation profile. There's so much flexibility with them.
I don't really want to go into how wonderful, but they are wonderful. But I was wanting to more ask, how involved do miners get in choosing some sort of energy storage? Surely most of the time they just go to somebody who does the energy for them. I mean, will they really be that involved with what the energy storage device does?
I mean, in early stages, they may do work themselves. They may come to a consultant like AECOM, and we'd look at their needs, and we'd consider what they're trying to do with the battery. And often it would head down a lithium-ion route when we're looking at spinning reserve type applications and off-grid. And for other applications where we're looking at load shifting, that's when we sort of shift to the right-hand couch over there and start looking at pumped hydro, compressed energy storage, flow batteries, and other technologies. But I think you've got to start, as has been said many times from the panel, that you've got to start from the need and what they really want to achieve before you even start thinking about what technologies you might want to pick from.
Yeah, I agree. It's coming up with that energy strategy and what's the long-term objective, and then fitting an energy mix, because as we pointed out, that energy storage doesn't produce any energy itself in its own right. It's an enabler and effective. It's an enabler of going to higher and higher levels of penetration of renewable energy on your system. So there needs to be an ultimate goal, and then structure the solution so that you can build towards that goal. You're probably not going to do it in the first year or the second year or maybe even the fifth year, but you need to build that flexibility into the solution, and it's probably going to start out with a spinning reserve. It's then going to start out with some generation shifting as you go to higher and higher levels of penetration and different forms of renewables on the system. Like we've heard conversations about how, yesterday in particular, how wind and solar complement each other really well, and then actually reduce the demands on the energy storage component, but enables higher and higher levels of penetration or utilisation of that renewable energy on the system. So that would be my suggestion. There's all the other things around demand profile, impact load response, or impacts that are going to be on that system. All those things need to be analysed, but I think really coming up with a plan of where you ultimately want to get to, which is ultimately driven by what the costs of technologies feeding into that are going to be, but having a good understanding of what the state of play is and where the pricing needs to shift to essentially enact the next step is a really important aspect of that analysis and that strategy.
I think it's a good point. The hurdle that we all are looking to get over is the cost one. And I think we've heard a couple of times today about the future carbon abatement risk. It's very real. And to not be factoring that into the modelling that's been done in this early energy strategy planning stage is missing a trick there around what can be done.
And don't assume that you know the pricing necessarily. I was talking to one of your competitors not long ago, and they said, oh, well, vanadium flow batteries are so expensive. And I said, well, do you know how much they cost? And he said, no. And then when I gave him the cost, he said, oh, gosh, I didn't realise. I'm like, no, because you're just listening to that. Batteries are too expensive. They need to come down in price. So find out the facts, I guess, is the thing.
I'm very relieved, Sam, that wasn't someone from AECOM. That was lucky. I think the other thing I wouldn't mind adding is have a look at your site. Don't overlook some of the energy storage assets that you have. And by that I mean the disused pits, the underground mine workings and caverns you're not using. These can all form integral parts of a pump storage or compressed air system and make a big difference in the economics. And there's plenty of mines out there that are looking at these options. But don't overlook what you've already got. It can lead you down a far more ambitious path than you maybe started out on. I think we've got enough time to go to questions, and it's been a very shy Western Australian audience over the last couple of days, so I'm hoping this energy storage topic proves me wrong. Oh, first hand up, brilliant.
We'll take your $1 billion.
Thank you, panel. Now, I have a question for large-scale generators. Let's assume I'm generating 100 megawatt of solar power. And I was given to understand if I have a storage of 100 megawatt, the cost is 1:1. So it didn't make sense that if I'm going to have 100 megawatt storage, then my cost is the same as the power plant. But then I thought, if we combine solar and wind, then I don't need 100 megawatt storage. Then you share the asset cost. And I would like to hear your views in how you reduce, because today the PV cost is coming down, so the ratio is 0.8 to 1, or even lower. I mean, every month, 3 months, you find the cost curve going down for solar. But your battery cost is not the cost of batteries, it's the total solution cost. So if we combine the wind with solar, then I presume you would not require 100 megawatt of storage. You could go down to 60 because it's only the balancing of the shift of power. So what is the panel view on this? Because that's going to make an impact on the industry.
It depends how much power you need to deliver. If you need to deliver 100 megawatts, then you're going to need to have your battery be able to deliver 100 megawatts.
Yeah, but then the cost is 1:1. So if you have at
Not
night
necessarily.
time,
You could do 100 megawatts with 700 megawatt hours if you wanted to be able to deliver that for 7 hours.
no,
makes
you're generating 1.1 million megawatt hours. So you need a storage for a continuity of supply.
I think it totally depends on, again, the term of phrase is use case. So what's your product? What are you looking to sell and who are you looking to sell it to and what are they looking to buy? So if you're trying to create a baseload product, a 24/7 product, I don't think there'd be any argument today up here that the technology and the batteries today probably aren't right for that. That's a mix. It could be a mix of wind and solar. Let others challenge me if they think otherwise. But if you're looking to create an afternoon peak product and time shift power from the middle of the day to the afternoon, well, you only need a few hours of storage because you're looking to dispatch. I'll make it up between 5 and 9, for example. So it all depends on what you're looking to do. And one of the good things now with the technology that we have is we can design products for consumers. So if somebody says, I want a peak product, then great, we can go and design a power plant for that. It's not like you're just trying to refit a power plant around an end customer's need. It can be designed bespoke. And the batteries give us that flexibility, which we just haven't had before.
Yeah, as an example, we can turn say 40 to 50 megawatts of solar into 5 megawatts of base load, and we do that by having 40 to 50 megawatts of solar, about 40 megawatts of compression to compress the air, but we only have about 5 megawatts of generation on the complete system, on the actual energy storage system. So we're collecting the solar when it's available for the 6 hours that we've got it. We store all that energy, but we then dribble it out at 5 megawatts. That gives us a 5 megawatt baseload product.
I think it's also a fair comment to say we're not seeing the drops in solar prices that we were seeing 12 months ago, 18 months ago. In some respects, there's been almost a bit of a dead cat bounce there with costs going up. And energy storage costs, in terms of percentage reductions right now, are far outstripping solar.
Hello, Anastasia Ploshkina, Directional Studies, South 32. I'd agree with John's on the economics of storage once you implement it. So at the moment it's cost, but if you're grid connected, that would be great to have some revenue streams accessible to storage owners as well. So alluding to this question, from your international and national experiences, which jurisdiction you found most receptive for the storage, energy storage owner, user, operator, and why that jurisdiction is your jurisdiction of choice? Thank you.
I can take a first. So a lot of it, so for grid connected, it depends on the tariffs. So like in Ontario, Canada, they have this super high demand charge that pays back really fast. So of course people are interested in it because the economics are so compelling. So for grid connected, I guess it's market dependent on the rules.
Yeah, in terms of battery energy storage, the biggest uptake again is driven by that tariff functions, and particularly UK have been installing a lot of battery for frequency regulation and spinning or essentially inertia applications. So it is driven purely by the market. I wouldn't say there's a lot of interest from energy storage companies in Australia because we have got the right settings here at the moment to enable a lot of grid-based energy storage coming online. There is a lot of uncertainty around policy and that will remain, I think, until we see what happens. So the biggest, I suppose, elephant is the Snowy 2.0 and where that goes and what impact that has on the storage market.
Korea is an interesting case in point because, like, of course, KEPCO is the monopoly provider there from generation right through to sort of distribution and retailing, but like they've put in 500 megawatts, and I think it'll end up at like a gigawatt of storage into their network, and it's been very successful. And they made a strategic decision that they'd actually roll out batteries into the whole backbone of the network, rather than putting in additional peaking stations as such. And I think that was just it was a strategic decision, but it's been very successful, as I said, and predominantly doing frequency regulation, but also doing like UPS and fault ride through, and it's demonstrated itself sort of even when there's been a fault in the nuclear power station, the batteries have been able to sort of carry through. So very, very impressive indeed. Yeah.
I think in Australia, it's the market that has the biggest spread between the high price and low power price. And so South Australia is probably that point at the moment. As more solar comes online, there is a question around, do you need more generation or more batteries? Is rooftop solar, utility scale solar, doing all the heavy lifting for a battery to justify the business case as that duck curve bottoms out during the middle of the day? So that's a question. And then for execution, it's truly just around the progressiveness of or the progressive mindset of your grid company who you're connecting with. And they're all very different, and some are embracing this and others are continuing to push back.
For vanadium flow batteries, it's China. China had a directive from the government which said that you have to install large energy storage devices, particularly vanadium flow batteries. So the largest battery in the world currently under construction is a 200 megawatt, 800 megawatt hour in China. So there are lots of huge batteries happening in China at the moment.
Warner Priest from Siemens. I guess the big question now is we've got hundreds and hundreds of megawatts of battery storage going into our system and probably a life of 10 to 15 years. What's going to happen when those batteries come to end of life? What costs are involved in recycling them or getting rid of them? What's expected to happen at end of life?
Ooh, well, that's a good one for me. 20 to 25 year plus, and at the end of the life, the vanadium electrolyte can be reused again and again and again and again and again. So that's what I think last year I said about using it as a tradable commodity rather than you actually owning the vanadium electrolyte. So you don't need to dispose of it at the end, but that's just us.
I'll also... Energy storage for stationary applications like this is about maybe 10% of the market for lithium-ion batteries compared to electric vehicles. So I think that we're going to see that there's going to be recycling that's going to gear up, and the automotive industry is already thinking about this, planning ahead. Recycling is getting better. It's not there yet, but we've got a little bit of a runway since these assets will last 15 to 20 years. But I think it's definitely a topic that people are addressing, especially automotive industry, and I expect the energy storage industry will get a ride on the back of the automotive industry a bit in the recycling.
I think too there's a number of components that make up a battery system. So, you know, all the batteries are just cells and they can be replaced. And you can even, there's functionality today and technology that's coming that'll enable you to change your power to energy mix, even with the same software. So it's not like the whole system comes to an end in 15 years. It's at the moment that's just is modelled on the degradation of the cell itself, not the power electronics or the inverters.
I think that's a good point, is if you do have an application which is going to run for many years longer than a typical cell life, factoring in those costs into your financial models now based on prices today is possibly excessively conservative. When in, say, 15 years' time, we're going to see big advantages in terms of cost reductions, but also in recycling costs coming down considerably.
Thanks, Craig. I think we have a last question in the back.
Yes, thanks very much. That was very insightful. It was interesting, the comments made about what they need and what they want to achieve, and then finding a solution and planning for it. Do you think there's a risk that with the solutions that are being offered that you can't keep up with with the demand and how quickly a lot of the mines want to set up and operate, given the short window that some of them have? So I come from a region where within 6 months we've now got 3 new mines, and they just want to operate, get product in, get the product out, sell it, make a profit, and then start investing money in research and development. So do you think there's a risk there's a mismatch?
Well, was it Will that was talking yesterday about redeployable solar? And there are batteries or energy storage devices of various sorts that can be redeployed. I won't start talking about vanadium flow batteries.
Yeah, I mean, I think there probably is a real risk. Certainly, I know that the deliveries like Samsung deliveries, LG deliveries are way out there, but we can give you some batteries. But yeah, no, it could be challenging, but it's a good problem to have.
Yeah, the deployment timelines on batteries is actually pretty fast because a lot of it's done off-site and then it's dropped to the site. So it's a matter of months for delivery. In terms of the lifetime mismatch, which I think you're saying if it's only going to be a 5-year life or a 10-year life, these are modular type solutions like shipping containers that can be moved from site to site. So you can imagine a scenario where one system is used across 2 or 3 sites over its lifetime to mitigate that risk.
Yeah, that's not the case for compressed air energy storage or pumped hydro type storage. We need long duration, and we're a bulk energy provider, long duration. So we're looking for large scale projects, large loads with large storage requirements.
Okay, I think we'll wrap up there for lunch. Thank you very much to the audience. I take back what I said about Western Australians being shy. There were some great questions there. So please join me in thanking the panellists today.